Hi everyone. So this is our collab 9. Here we are going to see neural networks from scratch with NumPy. So basically we will build a neural network completely from scratch using NumPy, no TensorFlow, no PyTorch, just pure mathematics and Python. So what we will learn: the neuron, the activation function, forward propagation, loss function, back propagation, building network, training and visualization, everything. So everything we will start from basics using pure mathematics and Python. So here we are importing the required libraries and printing the versions. Once this is done, we will move to the chapter 1, the neurons. So the neuron is where it all begins, from biology to mathematics. A biological neuron receives a signal through the dendrites and then processes them into the cell body and then sends the output through axon. We model this mathematically. So this is the dendrites. It processes them in the cell body and then through axons it uh, we give the output. So mathematical model we present it like this, where x is the input feature, w is the weights, b is the bias, and sigma is the activation function, and a is the output. So first we calculate the summation of weights, the summation where the weights are multiplied to the input feature and then the bias is added, and the result that we get from here we apply a sigmoid activation functions and then we get a output. So we will first define a single neural network. This is the fundamental operation in the neural network: multiply each input by corresponding weight and then sum all the weights and add the bias. So and then this is what we are doing here: we are doing the dot product of input and weights and we are returning the bias. So this is what a single neuron looks like. We have taken input as the first three array, and then we have taken the weight and we are taken the bias, and then we will pass all these things to the single neuron and it will give us the output. So this is very simple here: input, weights and the bias. So input multiplied by weight plus this bias will give us the output. So I'll just run it quickly, and this is the output. So now we know how neurons are set up. Now we will see the activation functions for adding non-linearity. So why do we need activation functions? Without activation functions, a neural network would just be a series of linear transformations. No matter how many layers we will add, the output would still be a linear function of the input. So that's why we need activation functions to introduce a non-linearity and allowing networks to learn the complex patterns. There are many activation functions, out of which we will going to see sigmoid, tanh, relu, leaky relu, and the softmax. We have already seen these functions in earlier videos, but let's see again how to implement them. So first we are defining a class activation function. This is the base class where we will define other functions. We have defined a forward to apply activation function. The derivative is to compute the derivative of back propagation, and this is the return. So we have this is the format of the class. Now we will define the class sigmoid, where we will pass the activation function, and then the sigmoid formula is this. So we will do the forward, where we will apply the formula 1 plus 1 divided by 1 plus exponential of the clip, and then the derivative. Similarly, we have defined the tanh. This is the formula for tanh, hyperbolic tangent. uh, these are the properties of that. Similarly, we have defined the ReLU. The ReLU is max of 0 to x. So for ReLU, what happens is, if the given value is less than 0, then automatically this function will return 0. Otherwise, it returns the x. Basically, it returns maximum of 0 to x from the value. So 0 and x is the value that we have passed. Leaky ReLU is one updated version of ReLU, where we also get some negative values, a small slope of negative values. And softmax, this is the formula. Softmax it basically gives the probability distribution where the sum of the all the values will end up to 1. So I'll just run this and the activation functions are loaded. Now we will visualize all the activation functions one by one and we will plot them. So if you see, this is the sigmoid, this is the 10H, this is the ReLU, and this is the leaky ReLU. So for sigmoid we have seen its range, and then this is the 10H. For ReLU, as we know, it will be either 0 or 1. So this is the dot dot line shows the derivative, where the derivative value will only be either 0 or 1. Similarly with the leaky ReLU, it's the same. So once this is done, we will move towards the loss function, measuring our mistake. So a loss function quantifies how far our prediction from true value, and during training what we want to minimize this and how we can do it. So the common loss functions are mean squared error, binary cross entropy, and categorical cross entropy, and these are the formulas defined for it. So we will define our loss functions. How we will define? We will define the loss function name. We will give the forward, computed the loss value, backward compute the gradient of loss, and then we will call it. So this is the basic plan of the class implementation. First we will implement the mean squared error. Mean squared error has this formula where we will do 1 by n into the sum of predicted value to the true minus true value, and then to the power of 2, and the gradient is dl by dy of the prediction, which is 2 by n of y prediction minus y2. So it is best suited for regression problems, and we have to penalize large errors. We have to do this. So we are returning the formula. This is the gradient in the backward. Similarly for binary cross entropy, this is the formula, and we are defining the formula in the forward and the backward propagation. And then we have this categorical cross entropy. This is the formula for the categorical cross entropy, and we are defining it in the forward and backward, and this is how our loss functions are loaded. I'll just run it, and now we will visualize the loss landscapes. So for this we have called our functions. We have true value and the predicted values, and we will call our MSE loss and BC values, and we will plot and see how it actually looks like. So mean square error, and this is our true value, and this is the binary cross entropy, and this is our true value. So mean square error is symmetric and is quadratic in shape, while BC is asymmetric and penalizes confident wrong prediction heavily. So this is what is our observation is from here. Now we will move forward to the dense layer neurons working together from single neuron to layer. So a dense layer connects every input to every neuron. So it connects every input to every neuron. Instead of computing each neuron separately, we use matrix multiplication that we have already seen. So we'll see how a fully connected dense layer. This is the workhorse of the neural network. Each neuron layer is connected every input, creating rich representations. So this is how we are performing the formula, and the same thing that we have seen in the formula we are implementing here. We are defining the forward function where we will do the dot plus bias, and then we will apply activation function, and for the backward propagation we will do the gradients. So this is the gradient activation, and then we will do the dot product sum, and then we will again pass the gradient to the previous layer, and we will quickly test it with one example, and I'll just run it. So a dense layer, we have 3 to 4 ReLU, and then this is the input shape, and we got this as the output shape. This is the weight shape, and this is the bias shape. So moving towards the back propagation, that is the heart of learning. How does a neural network learns? Learning is equals to the adjusting weights to minimize the loss. We need to know how much does each weight contribute to the error. The chain rule is the back propagation uses the chain rule to propagate gradients backwards. So derivative of L with respect to weight is derivative of L with by A, dA by dz, and dz by dw. So forward pass we already know z is equals to wx plus b. So we have this in forward pass, we have an input, then we apply this formula where we do z is equals to wx plus b, where w is the weight, b is the bias, and x is the input. Then we apply a activation function on that, and after that we get our output. So, and in the backward pass, we do the gradient where dl by w, we have defined the formula here, and this is the gradient descent update. So, once we have the gradients, we update the weights. How do we update the weight? We give the new weight is equals to old weight minus uh, new into dl by dw, where new is the learning rate. That is how big steps should we take. So this is about back propagation. So we have this optimizer class, um, where we have updated weights of all the layer. We have this HGD optimizer. This is the simple formula with optimal moment, and then uh, we have defined the formula same here. We have defined the weights and the biases, and then we are defining the velocity is equals to moment into velocities, and the learning rate is equals into the weights, and then again we are doing the velocities with respect to b, and then we are updating the weights. So we are computing velocity with the moment, and then we are updating the weights accordingly. And here we have this adam optimizer, where momentum is the first moment estimate, and is the second moment estimate of adaptive learning rate. And these are the updates that we do. In the first momentum, we will do beta 1 into m 1 minus beta 1 into gradient, and similarly we'll do for the way the second moment, and then we will do the bias corrections. So this is how we will do it. So we are defining all the beta 1 to epsilon, all the details, and we are updating, we are initializing the moment for the first update. Then we will update the weights, we will update the bias for the first moment estimate, then we will update the bias for the second moment estimate, and then we will do the bias corrected estimate, and then we will update the parameters. So this is how our optimizers are loaded. Once this is done, the complete neural network, we will put it all together. Now we will combine everything in a beautiful modular neural network class, where we will have input fully connected to hidden layers and one output. So let's see the neural network class. So this is a neural network class where we will have input, we will do dense plus activation into n, and we will get the output. So we will do forward pass, data flows left to right, we will do backward the gradient right to left, and then each class will be stacking, training and predicting, and training history of the visualization we will store the training history for the visualization. So first we will define the init function, where we have the layers, the loss, the optimization and history defined. Now in history we will store the loss, value loss accuracy and value accuracy. Now we have this add function where we will append the layers. We have this forward function where we will do the forward propagation of the output, and then we have defined this backward function where we will do the gradient work. We'll calculate the loss, and then we have this fit function where we will train the neural network. We'll epoch on this cycle for each bit, and this is what is happening. We will epoch the cycle on this batch, and then we have many batch for gradient descent, and then we will record every loss per epoch, and then we will compute the accuracies and store it in the history. We will store the loss also in the history, so that we can use it for the further graph plotation. So if validation, will also see the validation, will store the validation metrics in history, validation loss, validation accuracy, and we will print the progress after each epoch, and then we will at the end return the history. So this is how the whole uh, backward propagation, forward propagation, add, and the neural network class we have defined. And we have some more functions like predict, compute accuracy. For compute accuracy, we will see the predicted classes and the true classes, and we will provide the mean. And then for summary, we have this thing where we will print all the summary. We have the plot history function as well. We will plot the history using whatever we have stored during the training. So I'll just run it, and it says neural class loaded. Now let's train. First we will train it for learning an XOR. The XOR is a classic problem of a single neuron that a single neuron cannot solve because it's not linearly separable. That's why we need hidden layers. So we have this inputs and we have this XOR output. So let's see, we have this XOR input NP, this is second input. We will call the neural network class and then we will do XOR dot add and then we will see the summary. Once that is done, we will do the training and then we will do the text predictions and we will see the output and we will plot the training history to see how it is training. So if you see, we have this dense layer. We are printing the second dense layer and then we can see total parameters 32. The loss function is the binary cross entropy here and optimizer is Adam optimizer. We are doing epoch training and once the training is done we are doing the predictions. The predicted values are rounded off and then we are seeing this training and validation loss. Once after particular epochs you can see the losses gradually decrease to zero and increasing the epoch the losses decrease gradually, and with each epoch the accuracy is increasing and it's constant after a particular time. So this is we have this XOR. Now we will see the XOR decision boundary. We will plot it. So for this I'll just run it and you can see the decision boundaries of XOR. It's very clear and separated. The network learned to create a non-linear decision boundary. Without the hidden layer this would be impossible to create this hidden non-linear decision boundaries. Now second demo is the binary classification of moon's dataset. So we have to generate two interleaving half circle moons. So we have n samples per classes. We have this defined make moon function where we have the samples and the noises. We will divide sample per class by dividing it by 2 and then we are creating separate values and then we are taking the cosine and the sine values, and this is the first moon of class 0 and then we will define similarly the second moon of class 0 by taking the theta cosine of theta 1 and theta 2. So then we will combine it over a stack and then we will generate a random noise and then we will generate labels and then we will reshape it. So and then we will print the moon classification where we will call this function and then we will do permutations and then we will shuffle the data. Then we will divide the data into trained data and validation data. We are splitting basically the data here. Once that is done we will visualize the data using plot and then we will create a network. We will call the neural network class here. We are providing loss function as binary cross entropy and optimizer as Adam with learning rate as 0.01. So this is where we are creating the neural network and we are doing moon dot add dense layer with ReLU. Then we are adding second with ReLU and then we are adding the third dense layer is 16.1 and sigmoid. And then here we are printing the summary and then once that is done we will train our model and we will plot the result with the history. So I'll just run it and we can see this is the moon's classification, this is the two moons data set. You can see three dense layers, the loss function and the optimizer. The training is done. With the training the accuracy is increasing, the loss is the accuracy is increasing, and we can see with each epoch the loss has decreased and the accuracy has increased. We can see the non-linear decision boundary as well here. Now the next similarly the next demo is the spiral classification. We get some samples, we get the classes and the noise. We will divide into the samples per class. Again we will create some create spiral arms and we will define their sine theta and cos theta and then we will append them and we will store them in stack and array and then we will one hot encode them, and once that is done we will generate the data and then we will visualize it and we will see how it works, and then we will create a neural network with softmax function here. So here instead of binary we are calling the categorical cross entropy while creating the neural network. The optimizer is same, so we will add the three dense layers here, and then we will train the data and we will plot the history. So I'll just run it. So you can see this is the spiral data set, and we can see the three dense layers are here. We can see the categorical data, categorical cross entropy loss functions, Adam optimizer. We have seen the epochs, the training. Once the epochs are increasing, the loss has decreased, and once the epochs are increasing, the accuracy is increasing. So we will visualize the decision boundary of this as well, and we can see the decision boundary is very clear and spiral, and the final accuracy is 100%. The next demo is the MNIST digits, where we load the subsets of MNIST for demonstration, and we will use the sklearn digit dataset for simpler alternative. So we will import these files, and then we will load the digits and the target digit data and the digit target. We will normalize it, fit transform. We will one hot encode it with dot zeros and np arrange. We will split the data into training and test data. Once that is done, we will load the data with xtrain, xtest, ytrain, ytest, and ylabels from the load means sample. And once that is done, we will print the data. Then we will visualize some samples here. Once the visualization is done, we will create a neural network here. We are giving the loss function as categorical cross entropy loss and optimizer as Adams. We are adding three dense layers. We are printing the summary here, and then we are going to train with 100 epochs and bit size is 32. And then validation data set is x test and y test. And then we will plot the history and we'll see. I'll just run it. So you can see this is training samples, test samples, input features. We can see label 0, 1, 2, 3, 4. All these things are there. We have three dense layers. We have categorical cross entropy. We have training epochs. The loss is training loss versus validation loss. Again, the training accuracy versus the validation accuracy we can see. And the test accuracy is 97%. So we will see visually how it looks like, and then um, we can see how many times the prediction is correct, how many time it gets wrong, and the green ones are the correct and red ones are the incorrect. So conclusion, we have seen all these components of neural network, we have seen all these features, and now we are good to go with the neural network from scratch. And that's all for this. Thank you so much.